So here's the outline. In this chapter, we talk about the magnetic field, or more precisely, it should be called the magnetic flux density. But in this textbook, it called the magnetic field rather than the magnetic flux density. The magnetic field should be the H, rather than E. B should call the magnetic flux density. But in this textbook, it usually call it magnetic field. So we just keep this name, but just keep in mind B is the magnetic flux density. So, and then we'll talk about the discovery of the electron and so-called the Hall effect. The Hall effect. So the Hall effect gives us a hint that the moving electron, the moving charge should be an electron rather than a positive charge particle. And then we'll talk about the circulating charge particle, the cyclotron and synchrotron, the particle accelerator, and then the magnetic force on a current carrying wire, and the torque on a current loop, so on. So a magnetic field B can be defined to be a vector quantity that exists when it exerts a force Fb on a charge moving with velocity v. So v is direct perpendicular to that force Fb, and then the magnitude of B can be defined in terms of the force magnitude. So here, when we just ignore the direction, so we have B equals Fb over QV. So we ignore the direction, we only consider the magnitude. So we take the absolute value of Q here. So this is the magnitude of the B field. It's somehow like how we define the E field, but the difference part is that we also define the velocity of the charged particle here, because it is related to the magnetic field, or on the other way around, if the magnitude of the B field varies, it will change, or I should say, if the velocity of the charged particle change, the magnitude of the force will also change, which is proportional to it. So we also define this way to make this effect cancelled here. So B is the Fb over Qv, and the Q is the charge of the particle. And we can summarize all this result with the following vector equation. So writing it in a vector form is more smart. So here we have Fb, the vector Fb equals Q, V cross B. So B has the SI unit of Tesla. So the Tesla, the one who are compete with Edison, but the force we call the Lorentz force. Lorentz force on the particle by the field B is equal to the charge Q times the cross product of its velocity and the field, all measured in the same reference frame. We can write the magnitude Fb as this one. So Fb equals QVB sine phi. Phi is the angle between the direction of the velocity v and magnetic field B. So here we talk about the magnetic field, and mainly about the direction. So here, ouch. So here you can see that V is in this direction and B in this direction. So V cross B should point to the upper direction. V cross B should point to the upper direction. So you just use your hand to point to V and you cross to B. So your thumb will point to V cross B. So it is, I suppose you should have done it in high school. So I don't think it's very difficult. But this stuff will bother you for the rest of the semester. So here we need to concern is that you don't make it like this and then you rotate for more than 180 degrees and then you point to the other direction. You should guarantee this angle should be less than 180 degrees so that this one correct. And then you make sure you use your right hand because we always use the right hand rule. Don't use your left hand and then you get the result with a negative sign. Then it will be wrong in this class and in this course. So so actually let's see. So actually suppose we have V and we have B here. So V cross B should have a direction like this. So like this, go to the onto the upper side, and then the magnitude of V cos B should be the area of this one, area of here, and then psi phi. This one should be phi. So you know that when you learn the trigonometry in high school, so that you know this area of the triangle should be 1/2 V B psi phi. So for also this part, you need to multiply it by 2 so that it will be VB psi phi. So this is the geometric interpretation of the outer product or the cross product. And in the previous chapter, you have known that we have another operation called the dot product. Suppose we have A and B, and then the angle between them is theta. So that's A dot B equals A B cosine theta, which means that we have the projection. So this one is B cosine theta. So we have A B cosine theta. And similar to the inner product, we have we can write we can use the ijk vector for the outer product, for the cross product. So in this case, we have I cross I, I cross J, uh, I cross K, and then J, 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 I, J, uh, K, K, I, J, K. So we have totally line combination between them. So I cross I should be 0, J cross J should be 0, K cross K should be 0. And then we have I cross J to be 1, J cross K to be 1, K cross I to be 1. And then I cross K to be minus 1, J cross I to be minus 1, K cross J to be minus 1. So it's somehow like this, or you can write it like this, I, J, K. So I cross J should be positive. J cross K should be positive. K cross I should be positive. So for the other way around, this one should be negative. This one should be negative. This one should be negative. So if you just cross itself, it will be 0. So here we need to consider that we have V point to this direction and B points to this direction. So V cos B should point to the upper direction. If the Q is positive, then FB should have the same direction as the V cos B, so point to the upper direction. If the Q is a negative charge, then FB should have the opposite direction as the V cos B, so that FB points to the lower direction, So the force FB acting on a charged particle moving with velocity v through a magnetic field B is always perpendicular to V and B. So this one should be perpendicular to this one and also to this one. Because you use the cross product. The cross product means that they are also perpendicular to each other. Although V and B are usually not perpendicular to each other, but after V and B are crossed together, the answer should be perpendicular to both V and B. So here the figure shows 3 situations in which a charged particle with velocity v travels through a uniform magnetic field B. In each situation, what is the direction of the magnetic force on the particle? So for the first one, V points to the negative x-axis, B points to the negative y-axis. And this is a positive charge. So what is FB what is the direction of FB? So positive C, positive C. So for the next one, V points to negative Y. This is negative Z, and then is a negative charge. Positive X.
Oh, wow. This is not
Should be negative X because this is a negative charge like this. So this is positive Z. And then for C, V, and B. So this is no, none, none, because they are parallel to each other. Parallel to each other means the cross product should be zero, or the area of this V and B. The okay, maybe any questions? No. So maybe we just stop here.